Hello again and welcome to a new lecture in which we're going to discuss about rectangular components of a force and unit vectors. We're going to move now into the three-dimensional space, and let's consider a force acting in 3 dimensions, F. And what we can do with this force, we can actually resolve this force into its orthogonal components. And these would be, of course, Fx, Fy, and Fz. So, having said that, we can now calculate or express F as the sum of Fx plus Fy plus Fz. Now, let's define another set of vectors, orthogonal vectors, running along the x, y, and z axes. We're going to call these vectors I, j, and k. And what is specific about these vectors is that they have a magnitude equal to 1. So hence we call them unit vectors. Then we can write the x, y, and z components of F by multiplying the magnitude of the components by the unit vectors. So, as you can see, Fx equals to Fx times I, Fy equals to Fy times j, Fz equals to Fz times k. And hence we can express F as Fx times I plus Fy times j plus Fz times k, which is a very important expression of a force in 3 dimensions. It's also known as the Cartesian expression of F, or the vector format expression of F in 3 dimensions. Now, if we were to express the same thing in 2 dimensions, all we have to do is drop the term in k, the z component. So, in 2 dimensions, F will be equal to Fx times I plus Fy times j. Now, F makes 3 angles with the axes theta x, theta y, and theta z. And we can again express the components or the magnitude of the components of F, Fx, Fy, Fz in terms of these angles. So Fx equals to F cos theta x, Fy equals to F cos theta y, and Fz equals to F cos theta z. If we substitute the cosines with the letters L, M, and N, where of course L equals cos theta x, M equals cos theta y, N equals cos theta z. L, M, and N define the direction of F, so hence they're called the direction cosines of F. So therefore, in the end, we can express F as equal to F times L times I plus F times M times J plus F times N times K. And if we factor out F, this will equal to F times Li plus Mj plus Nk. Or we can call the expression in the parentheses vector lambda. So everything will be equal to F times lambda. And of course, lambda will have a magnitude of 1. So it is actually a unit vector directed along F. It actually defines the direction of F. So the direction of F multiplied by its magnitude gives F vector F. Now, what we will do next is we are going to simplify the problem a little and go into dimensions and apply Pythagoras theorem for a vector and its components in 2 dimensions. So if these are the 2 axes, x and y, you can see I draw them a little differently, and these are the x component and the y component of force F. which is the diagonal of this rectangle F, all acting at point A on particle A. Then by applying Pythagoras, we can calculate easily the magnitude of F of V as equal to the square root of the sum of the squares of the magnitudes of the components of F. And then we can generalize and express the magnitude of F in 3 dimensions by actually adding the component, the squared component along Z of F under the square root. So another important relationship to remember, the magnitude of a force in 3 dimensions by knowing the magnitude of its components. If we now go back to lambda, the unit vector along F, and express it as cos theta xi plus cos theta yj plus cos theta z times k, and we also know that the magnitude of lambda is 1 because lambda is the unit vector along F, we can square up this expression and we can say that 1 squared equals to the x component of lambda squared plus the y component of lambda squared plus the z component of lambda squared, or in other words, cos theta x squared plus cos theta y squared plus cos theta z squared equal 1. Always the sum of the squares of the direction cosines will add up to 1. Another very important relationship. So please remember these relationships, they're very important. So now let's see how we can apply these concepts to an example. A simple example in 2 dimensions in which we have a horizontal beam that is attached at its right end to a wall, and in order for the beam to be stable, it's also braced with a diagonal cable that is also attached to the wall. And this is the beam and this is the cable, of course. And the beam and the cables are joined at point A and attached to the wall, as you can see here, at points B and C. The horizontal length of the beam is 12 meters and the vertical distance between B and C is 6 meters. There's a force acting on the beam at D, and because of that force, the tension that is generated in the cable T has a magnitude of 10 kilonewtons, or in other words 10,000 newtons, again in cable AC. What the question requires is to express T, vector T, in Cartesian vector format. So in other words, in terms of unit vectors I and j this time. There's no k because the problem is in 2 dimensions. So let's select the axes of coordinates, x and y, and then we need to resolve t into its components, tx and ty respectively. And of course, the angles that t makes with the coordinate axes are x with the x-axis and theta x with the x-axis and theta y with the y-axis. We're going to start by calculating the angles. So theta x results straight away as being 26.57 degrees, and theta y, very simply, 63.43 degrees. Knowing the angles, we can calculate the direction cosines L and M. L being 0.894 and M being equal to 0.447. Now, at this point, it's very important to perform a check to make sure that the direction cosines have been calculated properly. And we're going to use the property that the sum of the squares of the direction cosines equals to 1. Well, it's equal to 0.99999, which is virtually 1. So we're okay, and we can continue with the solution. Tx, then, the x component of t will be equal to 10 kilonewtons times L, the direction cosine L, and hence the magnitude of Tx will be 8.94 kilonewtons. In a similar fashion, the magnitude of Ty, the y component of t, will be equal to 4.47 kilonewtons. Of course, we have to indicate their directions, so both of them are positive, as you can see. In the end, all we have left is to express t in vector format as equal to 8.94 times I plus 4.47 j, and don't forget about the units, which is very important. These are kilonewtons. So, as you can see, a very simple problem, but this is the way to approach these kind of problems. And I thank you very much for listening, and I'll see you at the next lecture.